So we have the equation, the square root of 5 minus x is equal to 5 minus x squared. And this looks like a fascinating challenge because right off the bat, you can see the symmetry hiding in plain sight. But before we dive into the beautiful logic behind this solution, I would really appreciate it if you could take a split second to hit that like button and subscribe to the channel because it really helps us keep making these math videos for you. Now, let's get back to the problem at hand. When you see a problem like this, your first instinct might be to get rid of that square root immediately by squaring both sides. And I get it, that is usually the standard move in algebra class. But I want you to pause and think about what happens if we do that here. Because if you square the left side, you get 5 minus x, which is fine. But if you square the right side, you're squaring a quadratic term, which means you'll end up with x to the power of 4. And suddenly, you're staring at a degree 4 polynomial, which is a nightmare to solve. And honestly, it is just an invitation for mistakes. So we're going to be smarter than that today and use a much more elegant method. But first, we have to set some ground rules, because in math, we can't just run wild without checking our boundaries. So let's define our constraints. Look at the term inside the square root, which is 5 minus x, and we know that in the real number system, you cannot take the square root of a negative number, so 5 minus x must be greater than or equal to 0, which means x has to be less than or equal to 5. But there's another constraint hiding on the right side of the equation. Notice that the right side equals a square root result, and a principal square root is always non-negative, which means 5 minus x squared must also be greater than or equal to 0. So if you solve that inequality, x squared must be less than or equal to 5, meaning x has to be stuck somewhere between negative square root of 5 and positive square root of 5. And keeping this valid range in mind is crucial because it'll help us filter out any fake answers later on. Now, here's the trick that makes this problem solvable and, quite frankly, beautiful. We're going to use substitution, but not just any substitution. We're going to exploit the symmetry I mentioned earlier. Let's introduce a new variable. Let's call it y, and we'll set y equal to that entire square root term. So y equals the square root of 5 minus x. Now, if we square this new equation, we get y squared equals 5 minus x. And if we rearrange this just a tiny bit, we can see that x equals 5 minus y squared. Keep that in your head for a second. Now, go back to our original equation. Since we called the left side y, the original equation becomes y equals 5 minus x squared.
Do you see what just happened? We have created a system of two equations that look almost identical. Look at them closely. The first one is 5 equals y squared plus x, and the second one is 5 equals x squared plus y, giving us a perfectly symmetrical system where x and y are playing the exact same role. And because both of these equations equal 5, we can do something very powerful. We can simply set them equal to each other. So we write y squared plus x equals x squared plus y. And this is where the algebra gets fun, because now we can move everything to one side to try and factor it. So let's subtract y squared and x from both sides to set the whole thing to 0, which gives us x squared minus y squared minus x plus y equals 0. Now, look at the first two terms, x squared minus y squared. That is a classic difference of squares, so we can expand that into x minus y times x plus y, and then look at the remaining terms, which are minus x plus y. If we factor out a negative 1 from those two terms, we get negative parentheses x minus y close parentheses equals 0. Now, look at the structure of this new equation. We have a common factor of x minus y in both parts. So let's pull that common factor out to the front, giving us x minus y multiplied by a larger bracket containing x plus y minus 1, all equal to 0. And this is the pivotal moment, because for two things to multiply together to equal 0, one of them must be 0, which gives us two distinct cases to solve. So let's break them down carefully, starting with case 1, where x minus y equals 0, which simply means x equals y. This is the easiest case, because if x equals y, we can go back to our substitution where we said y equals the square root of 5 minus x, and just replace the y with x. So now we have x equals the square root of 5 minus x. To solve this, we square both sides to get x squared equals 5 minus x, and then we move everything to the left side to form a standard quadratic equation, x squared plus x minus 5 equals 0. Now this does not factor nicely, so we need to summon our good old friend, the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our case, a is 1, b is 1, and c is negative 5. So, plugging those numbers in, we get negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 5, all over 2.
Let's simplify that. Inside the square root, we have 1 minus 4 times negative 5, which is 1 plus 20, which is 21. So our potential solutions for this case are negative 1 plus or minus the square root of 21 divided by 2. Now we have to check our constraints. Remember, x must be positive enough to satisfy the geometry here. But wait, if we look at negative 1 minus the square root of 21 divided by 2, that is a negative number. And if we check the original equation, checking x versus y and the original domains, we realize that specific negative value actually works mathematically, but we usually prefer the positive version in these symmetry cases. However, let's look at the specific valid root here, which is negative 1 plus the square root of 21 divided by 2. This is a valid solution that sits comfortably in our domain, so that is our first answer. Now, don't celebrate yet because we still have case 2. Remember that second factor we found earlier, which was x plus y minus 1 equals 0. This implies that y equals 1 minus x. So again, we go back to our original relationship where the square root of 5 minus x equals y, and we substitute this new expression in. So we get the square root of 5 minus x equals 1 minus x. Now we square both sides. Again, be careful with your algebra here. The left side becomes 5 minus x, and the right side is the square of the binomial 1 minus x, which expands to 1 minus 2x plus x squared. Now let's tidy this up by moving everything to one side to form another quadratic equation. So subtracting 5 and adding x to both sides, we get x squared minus x minus 4 equals 0. Once again, this does not factor nicely into whole numbers, so we bring back the quadratic formula for a second round here. Here, a is 1, b is negative 1, and c is negative 4. Plugging these in, we get negative of negative 1, which is positive 1, plus or minus the square root of negative 1 squared minus 4 times 1 times negative 4, all divided by 2. Simplifying the inside of the root, we have 1 minus 4 times negative 4, which is 1 plus 16, which gives us 17. So our candidates here are 1 plus or minus the square root of 17 divided by 2. Now, we have to be really careful with the domain constraints we talked about at the very beginning. Remember, we said x cannot be greater than the square root of 5, which is roughly 2.23. If you look at the option 1 plus the square root of 17 over 2, well, square root of 17 is a bit more than 4, so 1 plus 4 is 5, divided by 2 is 2.5, which is definitely larger than 2.23. So that solution is too big and it breaks our original constraint. So we have to discard the version with the plus sign, leaving us with the valid root for this case, which is 1 minus the square root of 17 divided by 2. So, after all that algebraic gymnastics and careful checking of our constraints, we have found our two winning solutions. The first one, from the symmetrical case, is negative 1 plus the square root of 21 all over 2. And the second one, from the asymmetric case, is 1 minus the square root of 17 all over 2. Isn't it satisfying how the method of symmetry breaks down a scary degree 4 problem into two manageable quadratic bites? Math really rewards you when you look for patterns instead of just brute forcing your way through equations. And that is our final answer, fully solved and verified. So if you managed to follow along and get those same answers, give yourself a pat on the back, because that was not a trivial problem. And if you got stuck somewhere, that is totally fine too, because that is how we learn. Please make sure to smash that like button if you enjoyed this explanation, and definitely subscribe for more math challenges just like this one. Also, I want to hear from you, so jump into the comments section below and let me know if you used a different method or if you have any doubts about the steps we took today. Thanks for watching, and I will see you in the next video. Class dismissed.